So there's not actually any attendees right now, but I want to go make sure that I have this up for you guys to review in case you weren't able to attend this morning, or if you attended and like you wanted to go back and review the material that we had covered about 55 minutes that we met. So I'm gonna go back and start where I started this morning, and let's see. Okay, first thing we did, we opened up a document which is on Blackboard now that Professor Waldron loaded, which is a series of examples of the kind of material that might be on the test on Monday, and we started to review a number of these problems. The first one, explain what 95% confidence interval means. Well, we discussed that was, the range with when we can be 95% certain that we have actually captured the real mean of the population mean. Okay, but you have references. Remember, this is an open book, so you have references that you can go to, that you'll have with you, or that you'll be able to access on Blackboard, that you can use for remembering what the assumptions are for various tests, what the definitions of various statistical phrases are, and so on and so forth. So make sure you have that kind of ready, and that you've gone through the PowerPoints and so on and so forth, to make sure that you're prepared for material maybe that doesn't show up necessarily in kind of problem reviews and stuff like that. Actually, we're talking about a little bit more stuff than we did originally this morning. Okay, so I didn't start with the proportions. I decided I wanted to start with something a little bit more direct. So I think we went to problem number 4, okay, to start off with. In a recent survey of 9 selected subjects who were identified as Buddhists, the following responses were collected for the number of hours daily spent watching TV. So they randomly selected 9 Buddhists. Again, this morning I said I don't know why they would want to know this, but that's the problem. And here's the results of the 9 samples, the number of hours that they spent daily watching TV. And they asked us to calculate an 80% confidence interval for the mean hours of TV watched by all U.S. Buddhists. Notice we're not interested in the mean of this sample. We're really interested in the mean of all U.S. Buddhists. Okay, so, but our only mechanism for estimating that is the result of the sample that we took. So we're going to have to work with this sample mean and use that to predict what the mean of the population is. That's really what this confidence interval stuff, and to a large degree hypothesis testing, is really all about. So I'm going to open up an Excel file. You can use you can use the calculator to do this. You can use some other mechanism to do this. You can even use SPSS or R if you are familiar with it to do this. Okay, but for our purposes, I'm going to use Excel just as a basically using it as a calculator. And I'm going to copy these 9 results. Okay, so there are my 9 subjects, and well, first thing I'm going to be interested in, what do we need to know to calculate a confidence interval, and also often to do a hypothesis test? Well, I need to know the mean of the sample, x bar. Right? We don't know the mean of the population, so that's going to be closest we're going to get. I need to know sigma, which is the standard deviation of the population. If I know sigma, that will allow me to calculate the standard error for the sample size I'm working with. I'm going to put sample size over there too. Okay, problem here is, well, if I work with sigma, if I know what sigma is, and I calculate my standard error, when I calculate my confidence intervals, when I do my hypothesis, when I do my hypothesis test, I can use the z-score, which is a more accurate way of calculating these various probabilities and whether to reject the null hypothesis or not. But I don't know what sigma is. The closest I can get to sigma is the standard deviation for this sample. We haven't been told what sigma is. So that means to us that we're not going to be using, since it's a small sample, smaller than 30, okay, and we don't know the population standard deviation. We have to rely on the sample standard deviation to approximate the population, just as we have to rely on x bar to approximate the mean of the entire population. Since we don't know that, We have to use the t-score or t-test, t-score, when we're calculating confidence interval. Okay, so now let's see what I got here. Sample size is 9. The mean is going to be equal to the average. Okay. Don't need that parentheses. Average. Okay, for this sample. Whoops, I made a mistake. Oh, no parentheses. There we go, that's better. The standard deviation is equal to the standard deviation of this sample. Well, we're using that to approximate sigma, but it's not going to be the same as sigma. The standard error is going to be equal to, we wish we know sigma, all we know is the population standard deviation, the sample standard deviation, divided by the square root of the sample size. Square root of sample size is 9. Okay, that's equal to 0.55. So now I'm going to calculate my 95% confidence interval. And I'm going to do that because rather than deal with this 80% and 95%, I'm going to call this 95%. And I'm going to say this is based on number of, watched by 90% of Buddhists, 95% of Buddhists. In other words, between the 2.5 percentile and the 97.5 percentile. In other words, there are 2.5% of the possible values from this population below that number and above 2.5% or above that number for a two-sided confidence interval, so that 5% are outside of the range that we're going to define. It's 5% chance of the mean of the population fall either lower than our range or higher than our range. Combined quantity of error is 5%. Okay, so I'm going to calculate this for 95% confidence interval for the moment. So how am I going to calculate that? Well, that's going to be equal to x bar, right? And it's going to be x bar minus some number, some multiplier, times the standard error. Well, what is that multiplier going to be? If we knew what sigma was, the population standard deviation, that would be the z-score, which represents a error of 2.5% on one end and 2.5% on 5%. Okay, that would be 1.96. 99% confidence interval would be 2.58. A 90% confidence would be 1.6. So I'm going to make this 1.96 because I changed the problem to 95%. Okay, now the upper range would be x bar plus 1.96 times the standard error. Okay, so let's actually do that calculation. Equals x bar minus 1.96. Oh, wait a second. I just made a mistake here, didn't I? I just said to myself, I don't know the population standard deviation. I only know the sample standard deviation, and it's not a large sample, not a sample larger than 30. So I have to use something other than 1.96. I have to make this interval that this margin of error, it's often called, this number that I'm subtracting and adding to the sample mean, I have to make that a larger interval so that I accommodate that extra level of error, extra amount of error that I have from not knowing the population standard deviation. So instead of using the z-score that would be appropriate for that confidence interval, I have to use the t-score. Okay, and how am I going to do that? I have to actually pull the t-table up. Here we go. Oh, I'm going to have to blow that up so we can see it. Okay, here's our t-table, and we have our 95% confidence interval, right? In other words, 2.5% chance of error on both the right tail and the left tail, adding up to 5% chance of error or 95% confidence. So I would go down here. Degrees of freedom are the sample size minus 1. Sample size was 9, so I go to 8 degrees of freedom, and the t-score that I need is going to be 2.306. I'm going to go back here And I'm going to change this to 2.306. And the same thing here, 2.306. Had a typo there anyway, right? Okay, so what's my confidence interval going to be? It's going to be equal to the mean, which is 1.5, minus 2.03, 2.306 times the standard error, which is 0.55. Okay, it's going to be equal to 0.27, and the upper bound is going to be equal to our mean plus 2.306 times our standard error, okay, which is 2.83. So we're 95% certain that the true number of hours of TV watched by, mean hours of TV watched by Buddhists, is between roughly 0.27 and 2.8 hours. Okay, we're 95% sure the true mean is between these two numbers. Okay, so now let's go back to this problem and look at it the way it was originally written, where it was 80%. I just wanted to do it first in a more familiar form, 80%, and that would mean that 80%, range where middle 80% of U.S. Buddhists watch TV, and that would mean that 10% low end, the 10th percentile, and the 90th percentile. That would be our range, because 10% error at the bottom, 10% error on the top, means 80% level of confidence in the middle. Okay, so now let's repeat this, except this time what's going to happen is it's the same sample size, the same mean, same standard deviation, same standard error. The only things that are going to change here now is what number we're going to use to multiply the standard error by. So let's see, I'm going to say, let's see, x bar, and I'm going to have to decide what that's going to be. Well, I'm going to go back to my t-table to decide what that t or z-score has to be. Again, small sample size. We don't know the population standard deviation, so we have to use t times the standard error, not z times the standard error. Okay, so let's see how we would do that. So I go back to this table, and sure enough, there is a column, as it happens, for a rather unusual calculation, nonetheless, something you might be possibly asked to use, and it's an 80% confidence interval. It's an 80% confidence interval, right? We use for 8 degrees of freedom, sample size 9, 8 degrees of freedom, we would use a number 1.397. So I'm going to go back here to my spreadsheet, my calculations actually, and it's going to be, my score I'm going to use is 1.397. So it's going to be x bar, right, minus 1.397 times the standard error, and x bar plus 1.397 times the standard error. Okay, what's that going to be equal to? It's going to be equal to, let's see, 1.55 minus 1.397 times the standard error, and the upper range is going to be equal to x bar plus 1.397 times the standard error, 2.3. So now notice our range is narrower than it was before. Well, the reason why it's narrower than it was before is because our margin of error, which is this combination of the t-score times the standard error, is often called the margin of error because you're adding it and subtracting it from x bar to give you the range within which you expect the true population mean to be found. Our margin of error is a smaller number because we're willing to have less confidence that we really capture the mean. So when we want more confidence, as the confidence interval gets to a larger percentage, 90%, 95%, 99%, the range of the two numbers, they're further apart to give us a wider range. So we're more certain we're going to capture the real, true population mean. And if we're willing to accept a lower level of confidence, then we can have a narrower range. Now, since it's narrower, we're less confident. We're 80% confident. The other thing that happens is that if we're forced to use a smaller and smaller sample size, the value of t gets larger, which also forces the range to be wider to make up for the level of uncertainty that's caused by the small sample size. Okay, so if you think about this, pretty interesting the way this confidence stuff works, right? Okay, so now let's see what we did next. Okay. Well, next, I'm not sure I got this in exactly the right. Well, I think we did proportion next. That's what we did. We went back here and did the proportion. We took a look at question number 2. Times Magazine quoted a poll from 2002 to 1,000 Americans in which they said 4% said that they were vegetarians. Okay. I'm making fewer errors here if we go this a second time. Ooh, tedious doing it without anybody watching. It's kind of weird. But in some ways, it actually works a little bit better. Unfortunately, there's nobody to catch my errors, so you'll have to tell me about them afterwards. Okay, so let's see what we have here. We don't know the proportion of all Americans that are vegetarians. We only know that a random sample of 1,000 Americans, 4% of them said that they were vegetarians. Okay, so I'm gonna say here, well, what do we know? We know p-cap. We usually put a little cap on top of that p to represent the sample proportion, not the population proportion, which is p. Okay, so that's p-cap is going to be equal to, 4%. It's going to be equal to 0.04. Okay, 4%. So now we want to calculate a confidence interval for that percentage. So p-cap is kind of analogous to our sample mean. So now in order to actually calculate a confidence interval, we need to know either a t or a z-score that we're going to use, right? Because it's going to be average plus or minus some number, t-score or z-score, times the standard error, times the standard deviation. You also have to know standard deviation, or actually, we really have to know standard error. It's really what we're after. Well, as far as t or z is concerned, right? When we're dealing with proportions, we have a few assumptions that we're making, besides the fact that they're randomly that were randomly selected. Okay, so one of those assumptions is that the sample size meets certain minimum criteria. That the sample size be at least 30 people, at least 30, and that each of the two groups in this binomial, in other words, binomials are you can have two values. Yes, they're vegetarians. No, they're not vegetarians. That each of those two groups has at least 15 individuals in it, 15 subjects in it. Okay. So let's see if this satisfies us. 4% of it. Well, we have a sample size of 1,000, so that's more than we need. Okay, and we have 4% or 4% of 1,000 is 40. So we have 40 people in one group. We have 960 people in the non-vegetarian group. So we satisfy both those criteria. Total sample size over 30. A minimum sample size in each group is 15. So we have a large sample. So we're going to allow ourselves, since that's going to be the rule we're going to set for every proportion that we deal with, we're going to allow ourselves to use z all the time instead of worrying about t for population proportion. Now for z, the 95% confidence interval is represented by a z-score of 1.96, as we know. So how do we calculate the standard error? Well, we had a document that we put onto Blackboard that you could use to calculate that you could use as references and so on and so forth. But just to recap, what we're going to do is we're going to call the standard error is going to be equal to the square root of, let me write it out a little bit over here first. It's the square root of, what's it going to be equal to? The square root of p cap, right, minus 1 minus p cap, times 1 minus p cap divided by n. The square root of this whole function. Okay, and you saw that as the square root of p cap minus 1 minus p cap over n. Take square root of the whole thing. Okay, so now we're going to actually calculate that here. It's equal to, and again, you can go back and spread in your PowerPoints and you can find that formula. Equals, okay, P cap is 0.04, I'm going to put parentheses there, equals the square root, and I'll put it let's see, P cap is 0.04 times 0.96, which is 0.1 minus 0.04, right? Divided by the sample size. Sample size in this case was 1,000. Okay, and let's see what we wind up with here. 20, the parentheses here. We'll put the parentheses here. Divided by 1,000. I think that'll work. Whoops. What did I do now? 0.05. Oh, it's okay. It looks like it. Whoops, I didn't do it right. That's not right. Equals, look at that, square root, parentheses, 0.04 times 0.96 over 1,000. Right, and let me see, maybe I'll add another parentheses there to make sure it does the whole thing. Narrative formula that let's get the correction. Point. I don't see what the difference is between what I'm putting there and what's up there, but okay, that's doing that. No, I don't want that. I don't. I want it to do. I want it to do the square root of the whole thing. What am I doing wrong here? Well, I'm going to do this in 2 steps. Rather than go nuts, 0.04 times 0.96. Okay, is that, and we have 1,000 is our sample size. So the square root of this is the top of our equation divided by this comes out to be 0.006. That looks like the right answer to me. Okay, I'm not sure what I did there in that formula that it didn't agree with, but funny, it worked out earlier, right? But maybe I'm doing this too long. Okay, so anyway, here we go. So now we have to calculate our confidence interval. Sorry for that stumble. Okay, so our confidence interval is going to be equal to P cap, just like before, minus what's it going to be? It's going to be our z-score, because we're dealing with a proportion in a large sample, 1.96 times our standard error. And what's our standard error? Well, our standard error we just calculated here. Okay, so let's actually go ahead and do this calculation. It's going to be equal to 0.04 minus 1.96 times our standard error. That's going to be equal to, that can't be, times 0.03. I'm doing something wrong here. Excuse me. Yeah, I see what I did wrong there. Our standard error was the top of our equation, not the whole answer. There it is. That's our standard error. So it's about 2%, 2.8%, right? And now I'm going to do the same thing. So we're going to add that margin of error is equal to P cap plus 1.96 times our standard error, which is calculated here. Okay, so our confidence interval, 95% confidence interval, for the true proportion of Americans that are vegetarians, based on this sample, is 0.028 to 0.052. Okay, now notice I didn't round anything until I got to the very, very end, because if I had rounded it back here somewhere, then as I multiplied and divided and found square roots and stuff like that, I would amplify my error by the time I got to the end, because I'm doing other functions that are based on it. Okay, so I only rounded if I really even bothered to. I mean, you could submit that as an answer, but even if I were bothered to round, I wouldn't do it until I got to the very end here. 0.028 to 5.2%. Okay, so that's the way I would handle this. Now, the actual problem, though, let's see. Okay, 95%. Okay, that's good. So we pretty much got through that. I think, with a little bit of a stumble. Okay, so I'm going to skip by that for the other part of that for now and go to problem number 4, which is another form. Now, it's nice that we're calculating confidence intervals, but really the basis for our study of all this was to get to the point where we're doing hypothesis testing. And in hypothesis testing, we're going to be confronted with a lot of different possible ways that we may have to do calculations. Okay, so for instance, on problem number 4, we have a situation where, let's see, not problem number 4. Let's go to just the down one. Okay, problem number 6. Management claims that the mean income for all senior level assembly line workers in a factory manufacturing MP3 players, I mentioned before, if you were there this morning, it seemed a little out of date MP3 players, is $350. A concerned client decides to test the claim for a random sample of 9 employees, and he finds their incomes. Notice we didn't make any kind of judgment. He wanted to know whether it was different than what the manager was claiming. Okay, he didn't make a judgment as to whether it was greater than or less than $350. So this might be like perhaps Apple's concerned about whether or not a Chinese manufacturer is paying his employees what he really says he's claiming to pay them. Okay, so we're going to test the mean of our sample against this claim of 350. So there's a number of different situations where we could get into where we do hypothesis testing. Some of them involve the main two groups of them, where we're dealing with numerical variables. Some of them involve single sample tests, and many of them often involve two sample tests. Two sample tests is when we're comparing two groups, this group of employees to say to another group of employees. In this case, we know the mean that's claimed, or the mean that the manufacturer claims represents the entire population is 350. And we're taking one sample to test that mean. So this is a single sample hypothesis test. Okay, so let's get now it happens to be two-sided because we don't know if the actual mean for the entire population is greater than 250 or less than 250. So let's go through. If you go back into the PowerPoint slides, there are, I believe, 5 steps that we recommend that you take in performing a hypothesis test, right? And among the first of them might be to set up your null and alternative hypothesis. So H null is going to be equal to, well, what is H null going to be? H null is going to be that that the true population mean is equal to 350. Okay. Now we don't have a second group. If we had a second group, we would say mu1 is equal to mu2 would be our hypothesis. Notice it's not x bar equals 350. We're not interested. I mean, we're using the sample mean x bar as a tool to estimate the population mean. But we're really interested always in what the population is, in estimating what the population is. And it's always an estimate because we never know what it is. Our alternative hypothesis would be that that the mean is not equal to 350. Okay, because we didn't make any assumption. Now we could have had a one-sided hypothesis where we said, well, you know, we think he's not paying them enough. So we're going to take the hypothesis that the mean, that we're going to make the assumption that the mean is less than 350, and that the alternative is that, excuse me, the mean is greater than 250, and that the alternative is that they're equal to or less than. In other words, we'll look at one side of that. But usually, for the most part, we take a more conservative approach, which is that it's a two-sided hypothesis. Let's prove that they're different. They could be different either way. 2.5% error on one side is tolerated and 2.5% on the other, rather than a 5% error in only one direction tolerated to reject the null hypothesis. So I'm going to go with a two-sided hypothesis here, as we usually do. Okay, and I'm going to say, okay, let's test this hypothesis. Well, before we test it, we have to decide what level of certainty that we want to test this hypothesis at. So we want to be pretty sure. We want to be at 95% certain. We're willing to accept up to 5% chance of being wrong, okay, or a type 1 error, type 1 alpha error of 5%. So alpha is going to be equal to 0.05. Okay, now presumably that would have been nice if they mentioned that in here, so we wouldn't have to do the so we wouldn't have to presume that we wanted it at that level of certainty. Okay, so let's go ahead and do our test. Okay, so what we're going to do is we're going to compare the mean that the manufacturer claims to the mean that we've actually calculated in our sample. In other words, we're going to look at mu for the manufacturer minus x bar for our sample. And what are we going to be interested in there? Well, what is that? That's equal to, let's see, I have to calculate now what the mean for our sample is. Okay, so let's go, let's list these numbers. 350, 330 rather, 350, 340, 360, 320, 330, 350, 340. Okay. Okay, so what's the sample size there? Sample size is 8 in this case. So what's our mean? Our mean is the average of these numbers. Okay, happens to come out to be 340. That's x bar. Okay, what's our standard deviation? Well, we would love to know sigma for the entire population. Unfortunately, we don't. The only clue that we have to the variability of these salaries is our sample. So our standard deviation, not sigma, not the Greek letter sigma, but our standard deviation is going to be equal to standard deviation of this sample. Okay, there's our standard deviation. Remember now our sample size was 8. Okay, so now I have to calculate, let's see, we were looking at what's the difference between mu that he claims and the closest estimate we have of the real population, which is x bar. What's the difference between those two? Well, the difference between those two is, let's see, he claimed 350, and we found x bar to be equal to 340. So it's $10, whatever that is, a month, a week, or whatever, right? So it's $10. Now we have to determine, gee, are those two numbers far enough apart for me to say that the mean that he claims and the mean from this population we draw our sample are different enough? How many standard errors apart are these? Okay, so now I got to calculate my standard error. What is my standard error? Well, my standard error for repeated samples from this population estimated by this sample is going to be equal to, how do we calculate that again? That's going to be equal to, it's going to be equal to our standard deviation divided by the square root of the sample size. Square root of the sample size was 8. Okay, so our standard error is 5. Okay, so now, let's see. Okay, good. So now I have to determine how many standard deviations apart these two values are. Okay, so now I'm going to say to myself, did I get all those numbers right? Let's check. 340, 350, 330, 320, 360, 340, 330. I think so. Okay, so I'm gonna go ahead and check this. I'm gonna say how many standard errors apart are these? In other words, my z-score or my t-score. Well, now which one is it? Is it going to be z-score or t-score? Well, if it was z-score, I'd be looking for a value that would be greater than 1.96, because I know that 1.96 represents 95% confidence interval. That number of standard deviations apart, it represents 5% chance of being wrong if I reject the null hypothesis, or less if it's larger than that. So my critical value, if it's z, is 1.96. But I can't use z because my sample size is small, and I don't know the population standard deviation. I have to use t instead. So if I use t instead, well, let's calculate what t is going to be for this situation. Well, t is going to be equal to mu, I'll draw it here, mu minus x bar over the standard error. Okay, in our case, what is t going to be equal to? It's going to be equal to 10, which is mu minus x bar, divided by the standard error. The standard error is approximately 5. I'm not sure if that rounded in that spot or not. So this t is equal to 2. I got a little bit different answer than I did before. Maybe I got before I did it before I messed up one of these values. Okay, so my t value, I think in both cases though, same thing's going to happen. Our t-score is 2. So in this case, well, let me think about this. T-score is 2. Well, how big does my t have to be for me to reject my null hypothesis? Well, I need to go to the t-table. Here's the t-table. Okay, here's the t-table, and my confidence interval, 95. Well, the level of error in each test that I'm willing to accept, since it's an alpha of 5% and it's double-sided, two-sided, well, it's 2.5% chance of error in the right tail and 2.5% in the left tail. So I'm going to be using this column, right? And if I go down to, let's see, 8, sample size is 8, degrees of freedom is 7, our t-score, critical t-score, is going to be 2.365. Okay, so our critical t-value is 2.365. Okay, so now I have to make a judgment. Does my t-score for this distribution represent a number that's bigger than my t-score that I need to reject the null hypothesis? The answer to that clearly is no. So what happens here? I fail to reject the null hypothesis. Now, had the t-score been bigger, I would have rejected the null hypothesis and accepted the alternative hypothesis. Notice that I don't say, because I couldn't reject it, I don't say I accept the null hypothesis. Right? That's wrong, because I have no judgment. I'm attempting to reject the null hypothesis. Just because I didn't have quite enough evidence to reject it doesn't mean the null hypothesis is true. So we don't say that. We say either we fail to reject the null hypothesis or we reject the null hypothesis and accept the alternative hypothesis. We never say we accept the null hypothesis, if that makes any sense. I hope it does. Okay, so that was an example of a single sample t-test. Okay, it was t instead of z. If we had done z, if it had been a large sample size and we knew the population standard deviation, we could have used 1.96 for the critical value of z. In fact, we could have even gone to the z table for whatever t came up to be, whatever the value that came up to be for the number of standard deviations apart, standard errors apart, the two values were, two means were. And we could have gone to the z table and actually calculated an actual p-value or number. Okay, so, but I wasn't able to do that in this case. In most real-world cases, you can't do that. You got to use the t-score. But okay, on an exam, it might come up. Perhaps tomorrow's session, Sunday session, we'll do an example like that, where you actually calculate the p-value using the z-table. Okay, so I'm going to move on to another example, which is, let's see what I've done so far.